Okay, I'm back. Almost last topic, DC motors. I'm going to go through how to solve these. I got 3 DC motor problems here. They're really not all that bad. Let's go ahead and take a look at it. First things first, I'm going to look at this first problem. DC permanent magnet motor operated at 15 volts, has torque listed at the table to the right. Well, that table doesn't exist, but don't worry about it. And plotted below. So there's a very standard procedure for going through this. First thing first, if you don't have the points, plot them. If you do have them plotted already, like this problem is, then take a straight edge, otherwise known as a piece of paper that you fold along one line, line up the dots, and draw a straight line through them. And there's a reason for that, which I'll get around to in just a moment. That looks like a pretty good straight line, right? What that tells me is some particular features. One is the stall torque. I know what the torque is at stall. Another is the no load speed down here. I know what the speed is when there's no load on it. There's no torque. So I'm going to write that down. Omega no load is equal to 3,000 RPM. Remember, that's rev per minute. And tau stall is equal to 4 inch-pounds. So there we go. 4 inch-pounds and about 3,000 RPM. From there, everything kind of falls into place as we go through. All we've got is if omega no load is equal to 3,000, and I'm going to write it down as rev per minute, and there's a really good reason for that, and that is that I'm not going to forget to multiply by 60, well, divide by 60 when I convert from minutes to seconds, but we'll get back to that, I guess. What we've got going on is the DC motor, the circuit, you've got the input voltage, Vn plus minus, like that. You've got I times R plus minus. You got KB times omega, plus and minus. And if we start off at this point, we go up over Vn, we go down over IR, and we go down over KB omega, and we're back over here. KB omega is the back EMF. So you have Vn minus IR minus KB omega is equal to 0. Now, the reason that this is a straight line is we also have a relationship that K sub A times I, the torque constant times I, and sometimes we say I sub A and R sub A, I guess I'll do that, trying to keep this straight, is equal to tau in motor torque. That is to say, torque is directly a function of torque is a function of current. Now, if we felt like it, what we could do is we could say, well, hey, that says that I is actually equal to torque divided by K sub A, the torque constant. And I could plug that in right about there. And that tells me that my input voltage, which is constant for operating condition, minus tau R sub A over K sub A is minus KB omega is equal to 0. Effectively, what we can do is we can solve out for torque in terms of speed and voltage. So let's switch sides of the equation. Torque times RA over KA is actually equal to then, let's see, I'm going to write it this way, minus KB omega plus Vn. The reason that I write it that way is that now I have torque is equal to minus KB AA times omega. This is over RA. I'm going to put that in parentheses. I might even put the negative on the inside of the parentheses as well. And I'm trying to make a point. Plus Vn over RA times KA. There's so much to be seen out of this when you're looking at it the right way. We said over here torque is current times torque constant. Vn over Ra is the current that you would get if there were no back EMF, if it was not spinning, if you have voltage divided by the resistance of the motor is all the current that you provide, multiply that times the torque constant, this actually is your stall torque. And that's what you would get in the absence of the motor spinning. The fact that the motor does spin, you get this kV times omega, a back EMF voltage. So once again, that's a voltage divided by resistance is current times torque constant gives me a torque. So this is a quantity that's subtracted from the stall torque. If you get less than the stall torque at any place where omega is non-zero. And you also see this in the form y is equal to m times x plus v. The y-intercept v is the stall torque that I just told you about. This is the slope. It's a negative kV Ka over Ra. X is the independent variable of speed as you move up and down. And then torque is what we're going to get out. So that gives us this curve that you see there, torque, omega, like this. And we get these two operating points. Now this operating point, like I said, is VA over RA times KA. That's the only place where you'll actually ever see the current voltage divided by resistance. Anywhere else on this curve, voltage divided by resistance will not give you the correct current. You've got to go ahead and figure out, well, if this is torque, then current is torque over Ka. You divide everything by Ka in these equations, and you'll see that Kb times omega over Ra is going to be current that is subtracted from your Vn over Ra. And again, we're going to divide by, we can manipulate that equation if we want to. We want to figure out what current is. We say that current is equal to torque divided by the torque constant. Now over A sub A is equal to minus Kb omega over Ra plus Vn over Ra. And again, this is the current you get at stall, and then there's some component that is subtracted from that, which is why you only get the maximum current. You get the maximum current up here when the motor's not spinning. And for that matter, down here, you get zero current as you move along that curve. So if we get that curve, the way that we can backtrack and figure out what's what, we have a number of relations we can use. One of them is this. If omega no load is 3,000 rounds per minute, Kb times omega no load is the voltage. And let's go ahead and take a look at, say this equation. If the torque is zero, torque is only zero there, this quantity is zero, that says Kb omega negative added to Vn is equal to zero. In other words, Kb omega no load, that's a particular, so that's not just omega, that's omega no load. In particular, this is the particular omega no load right there. Kb times omega no load is the applied voltage. If you double the voltage, then you'll double the no load speed. If you cut the voltage in half, then you'll cut the no load speed. And so, if this is a curve that's associated with some fixed voltage, say 10 volts, and then you were to drop it down to 5 volts, you get this curve. If you were to crank it up to 15 volts, you get that curve. So, what that tells us then is that K sub B is equal to the applied voltage divided by omega no load. Is equal to, well, in this case we had 15 volts divided by 3,000 rev per minute is equal to, let's see, 15 divided by 3,000, 15 is going to cancel out what that was, 1 over 200. 1 over 200, that would be volts a minute per revolution, which is a really bizarre number, but there's a point to that actually. Let me get to that in a second. It's volts per RPM, 1/200th of a volt per RPM. Let's see, 1/2 is 0.5. Is there 1.005 volt minute per rev? And just to make sure I'm not dropping any zeros, just for good and giggles. Yeah, I don't know, pathetic to be able to have to do that, but let's see. 15 enter, 3,000 divided by, okay, volt minutes per rev. Now that's a strange read. It's essentially saying 5 millivolts per RPM. You could do that. You could say I prefer putting it as volt minutes per rev because, to be honest, even though K sub B is equal to that, I'd rather put it in radians per volt seconds per radian, or volts per radian per second. So I can actually go ahead and do 0.005 volt minute per rev times 1 rev per 2 pi radians times 60 seconds. You multiply by 60, not divided per minute. Minutes going to cancel out, revs cancel out. Now we have seconds per volt seconds per radian, otherwise known as volts per radian per second. And so what I'll get in that case is 0.005, 60 times 0.005, enter 60 times 6.28 divided by, missing units, got 0.0477. 8, why not call it that? Actually, 0.0478, let's just do that. Volt seconds per radian is equal to 0.0478 volts per radian per second. So for every radian per second of speed that you got, you'll get almost 50 millivolts. You get 47.8 millivolts of back EMF. Now the reason that I put it in that form is that I know for a given motor, if I'm using the metric system, that the value of K sub A, while the units are different, the value will be the same as K sub B. So it's 0.0478 newton meters per amp. That's a key element of what I need, because up here at stall torque, if I know the applied voltage, and I know the stall torque, and I know the torque constant, then I can figure out what the resistance is. So, to that end, I go ahead and I say, okay, I stall times R sub A, let's see, let's not do it that way. K sub A times I stall, that's the torque at stall, is equal to the applied voltage times K sub A. Well, that's interesting. Yeah, okay, forget it. Sorry, that works. My bad. KA stall is equal to VA over RA times KA. Kind of brain fart. I guess I'm kind of getting a little tired of doing the videos. What's happening here, though, is we don't know I stall. That's what I was trying to say. This is actually going to be torque divided by K sub A. Okay, tau stall divided by K. That is, I'm sorry, once again. Torque divided by K sub A is I. And so I times Ka and all that stuff. So tau stall is VA Ka over RA, or RA is equal to V sub A Ka. Now that's one way of looking at it. Another way of looking at it is saying, okay, I know that my stall torque divided by K sub A is equal to I stall. And I know that I stall is equal to VA over RA. The only time it says voltage divided by resistance. So what I can do is take T stall divided by KA to get my current, and then that current voltage divided by that current gives me the RA. It's manipulating the same equation. What we get is this: VA KA over tau stall. And so this in our case is going to be 15 times 0.0478 divided by, what did I say T stall was? About 4 inch-pounds. There is our problem, isn't it? Trouble is, this one is newton meters per amp. And this one's in volts. That's no problem. Newton meters per amp is no problem. That's the problem. 4 inch-pounds force. Don't do that. Okay, so how do we deal with that? Well, probably the easy way to do it is to say 4-inch ounce force times 2.54 centimeters per inch. Those cancel out. Times 9.81 newtons per 2.2 ounce force. Remember, if you went through the second order systems, what I said was that the weight of a kilogram is roughly 2.2 pounds, and it is exactly, within some accuracy, 9.81 newtons. So what we have then is that the torque in foot-pounds, inch-pounds, is going to give us this other number. Let's see, 4 enter 2.54 times 9.81 times 2.2 divided by 45.3 Newton. Almost. That's Newton centimeters, right? Like I said, I get a little tired from doing these videos. Let's see, times 1 meter per 100 centimeters. Now I can cancel out the centimeters there, I cancel out my pounds force, and I'll have Newton meters. So 0.453 Newton meters. 4 times 2.5 is roughly 10 times 9.81 is roughly 100 divided by 100, 1 over 2.2. Yeah, that works about right. I can live with that. So this is our torque that we actually get. We put that in here, 0.0453. And so let's see, 100. If I take 0.0478, okay, and I multiply that by 15 and divide by 0.453, 1.5. Alright, I'm going to double check myself here just for a second. Let's see. We do 4 enter 2.54 times 9.81 times 2.2 divided by 100 divided by 1 over x, 15 times 0.0478 times 1.58. Yeah, 1.58 ohms. That's the resistance of the motor. So what we've done is we've determined the vacuum F constant, and we got the motor torque constant and the motor resistance. Let us suppose further two things. Let us suppose we want to find the power of the motor at a given operating point. Let's pick a nice clean data point. I suppose let's go ahead and pick a data point in the middle of the curve. Yeah, let's do this one. I'm going to pick power at this point. Okay, let's pick the power up there. What I need to know is that right about there I have about 3.1 inch-pounds of torque. I also know that my speed is about 750 RPM. Now, so I get those numbers. That's what I'm going to be playing with. So torque times speed is power. And then the electrical power is voltage times current. It is not I squared R. Not in general. Let me get a different marker going here and we'll see what we can do here to that end. I'm going to leave up some of these parameters. My resistance to the motor, that's important. What else? KA and KB, those are important. Everything else here, not so important. Probably need to rederive that equation before we can get the second answer question. So, let's see. Torque is equal to 3.1 inch-pounds force times 2.54 centimeters per inch times 9.81 Newtons per 2.2 pounds force times 1 meter or 100 centimeters is equal to. So let's work that out. What do we have here? 3.1 enter. 2.54 times that. 9.81 times that. 2.2 divided by 100 divided by 0.3511 watts. No, it's not watts. What am I saying? That's Newton meters. Okay. There's actually a much easier way to do this, by the way, but we'll take a look at it in a second. So this is torque. Omega is equal to, I said, 750. And that's revs per minute times 1 minute per 60 seconds times. Yep, okay, got that. Times 2 pi radians per revolution is equal to, well, we're going to get rid of our revs, we're going to get rid of our minutes, we'll have radians per second left. We have 750, enter, 6.28 times, that's our 2 pi, 60 divided by 78.5 radians per second. So, P out is equal to tau times omega is equal to 78.5 times 0.3511 is equal to 27.6 watts. Now what's P in? It's V times I. It is not I squared R. The only time that a motor ever sees I squared R power delivered is at stall. In which case the output power is 0, in which case you have 0 efficiency. And that's ultimately it. Did I forget to say that? I'm trying to ask actually what the efficiency is at this 750 RPM speed or 3.1 inch pounds of force. So if this is V times I, you've got to figure out what I is. Well, actually, that's V times, well, now we have torque divided by torque constant. Torque over K sub A. Okay, that's how we figure out the speed. We know that we got 15 volts. So, Pn is 15 volts times our torque, which we already evaluated was 0.3511. Okay, and that was Newton meters. And then we're going to divide this by our torque constant of 0.0478 Newton meters per amp. And so what we've got is volts times amps ultimately, so that's power out. So let's see, I go 15 enter, 0.3511 times 0.0478 divided by is 110.2 watts. Okay, P out divided by P in. Zeta is equal, or eta, or whatever efficiency is, 27.6 divided by 1110.2 is equal to 0.25. You could say it's 25% efficient. That's one way of doing it. Now, this actually leads to another interesting expression. If P in is V times I, which is V times torque over Ka, and P out, is that going to come through? Not terribly well. I'll write it down here, I guess. I'll just have to remember 1.58. P out is equal to torque times omega, like that. Then actually, efficiency, which is P out over P in, is actually equal to tau omega divided by V times tau divided by K sub A is equal to K sub A omega over V. Is that right? I think it is, but let's try it out. Okay? So what I'm now saying is that eta is equal to, or whatever that Greek symbol is, K sub A, which is 0.0478, 0.0478, times the speed, which was 78.5, divided by 15 volts. And this is what we got. I'm going to leave off my units here. You should not, because you might, I don't want to get wrong with the test and all that. Newton meters per amp, readings per second, volts. I get 0.0478, enter 78.5 times 15 divided by 0.25. Well, you know, I get the same answer both ways. So to be honest, the P out over P in this approach, you just need to know the torque constant, the speed and radians per second, and the voltage. The torque constants in Newton meters per amp, of course. So units, units, units. These problems are about units. Last question about this, and this one's a little more kind of hypothetical type thing, but it's not hypothetical, it's analytical. I don't know what you want to call it. If we have, let's try this, by the way. Now let's leave that off. I'm not going to bother doing that one. That was going to be a little derivation. I'm not going to do that one. That one wanders off into the distance. Let's see. I'm trying to teach you how to do these motor problems, and that was, I think, a good example. Let's see, other motor problems. The second problem I'm not going to work through. Okay, you can do this one. It's got the same two data points. Draw that curve, figure out your no load speed, figure out your torque, stall torque, and so I kind of try to write the breadcrumbs here, get the stall torque, get the no load speed, get the back EMF constant from the no load speed, get the theoretical resistance from the stall torque and the other relations there, including once you get the back EMF constant, that gives you the torque constant, and then get the efficiency. Remember, units, units, units. Units are important on these. The last problem is this one. Let's see, how do I want to do this one? 60 volts and a speed of 1035. It develops 45.2, and this is problem number 3. 45.2 inch-pounds of torque when operated at an armature voltage of 60 volts and 1035 RPM. Yeah, little units, trying to make points on units here. So, let's write this stuff down. 45.2, and that's at 1035 RPM. You get this, not stall, it's at 1035 RPM, you get 45.2 inch-pounds force. So you multiply that one times, once again, 2.54 centimeters to the inch times 1 meter per 100 centimeters times 9.81 newtons per 2.2 pounds force, and that will give you the torque in Newton meters. Okay. Let's see. 45.2, enter 2.54 times 100 divided by 9.81 times 2.2 divided by 5.11, actually 5.12. Let's just round, let's stick with 3 decimal places. 5.12 millimeters. 1035 rev per minute times 1 minute per 60 seconds times 2 pi radians per minute is equal to 1035, enter, 6.28 times 60 divided by 108.33 radians per second. Okay, so we got the torque and the speed, and that's 60 volts. Okay. We also are told by the manufacturer that we get a stall torque of 8 newton meters out of voltages at 60 volts. Okay. So what I'm going to do is draw that 8 newtons on here at stall, and then at 1035 RPM, which is equivalent to 108.335, I'm going to draw 5.12 newton meters. Wow, it had quite the drop here. And roughly, those are the data points that I get. This is the stall. And this is the one that's out at 108.335. So not quite 110 radians per second, and a little over 5 newton meters. Okay, it's rough, but it's there. Oops, marker came apart. There we go. Let's see. Take a straight edge. Oops. Yeah, pen worked out okay. And this is what I get. That's my torque curve. Looks like my no load speed. I'm gonna make my life easy and call it 300 radians per second. Like that. And my torque is going to be my stall torque again. 8 newton meters, like that. So that's what you get. So, what the question asks for are what are the torque and efficiency if you operated at 35 volts and 1250 RPM. That's different. We're going to have to mess around with this just a little bit. What we can do, maybe what we should do is ask ourselves, what is it that we really want? We want 35 volts and 1250 RPM. $12.50 rev per minute times 2 pi radians per rev times, I keep getting that one backwards. And that's why I always put the minute rev per minute like that. Okay, so it's going to be, I don't know, somewhere on the order of 130 or so. There's maybe 135. Because you're roughly dividing by 10. 6.28 divided by 60 is, I don't know, what is it? 6.28, enter, 60 divided by, multiplying by 0.105. So you're dividing by a little more than 10. 1250 times 130.8. Radians per second is equal to omega. And in this problem, I'm going to do this. I'm going to do it the right way, I guess I should say. P out. P in. We're asking for what's the torque at this point, and so that, I suppose we should do that too. But this is the shortcut. This is the easy way to do it. If you memorize this, I don't know if that's a good idea. I think you should figure out how to do this. This is equal to torque times speed divided by voltage times current. Okay, I was just checking myself there for a second, which is equal to Ka times current times omega, that's torque times speed, divided by voltage times current. Cancel, cancel is equal to Ka times omega over voltage. All right, so that's an easy way to do this. But we don't know Ka. Or do we? Well, we know 60 volts gave me a no-load speed on this plot. Okay, 60 volts gave me 300 radians per second. 300 radians per second. Oops, I won't do it up there because I think I glare from that thing. 300 radians per second times K sub B is equal to the applied voltage. This is at 60 volts. It's not at 35 volts, it's at 60 volts, okay? You've got to keep that in mind. Therefore, K sub B is equal to 60 volts. And I shouldn't even put in V sub A. I should say that's equal to 60 volts. So, K sub B is 60 volts divided by 300 radians per second is equal to, let's see, that divided by that divided by that, 1/5, 0.2 volts per radian per second, or volt seconds per radian, however you want to look at it. And that means that K sub A is equal to 0.2 newton meters per amp. Okay? Aha, I'm the calculator. So what do we have? 60 enter 300 divided by 0.2. Just wanted to double check in case I'm screwed up on that. And so the question is asking 35 volts, a speed of 1250 RPM, 1250 rev per minute times 1 minute, 60 seconds times 2 pi radians per minute, minutes, 2 pi radians per rev. It's time to take a break here. And so this is equal to 1250 enter 6.28 times 60 divided by. God, I did that, didn't I? There really is time to take a break, isn't it? 138 radians per second. Okay, so this is equal to 0.2 times 130.8 divided by 35 volts. Okay, so we go 0.2 times that, 35 divided by 75%, 0.748. Well, as I say, in our dreams, I don't think they're going to get that kind of efficiency. Those were contrived numbers and perhaps a bit optimistic. That's one way of looking at the problem. Another way of looking at it is, okay, if I've got this 0.2 newton meters per amp, then what I can do, I can ask, well, I guess there are a number of things I can do here. One other thing I can do is I can use my chart and I can ask myself what kind of torque I'm going to get at 35 volts. What I can do is I can say, well, look, if this is 300 radians per second is omega no load for 60 volts, then omega no load at 35 volts is equal to omega no load at 60 volts times 35 volts over 60 volts. I know that because it scales. That's the equation of that line that I showed on that prior problem. So what I can do is I can take 300 divided by 60, which of course is going to be 5, times 35 is going to be what? 175 radians per second. Just to double check, 300, enter, 60 divided by 35 times 175 radians per second. That's what you get on that one. Omega no load and all that fun stuff. And also, stall torque, 35 volts, is equal to stall torque at 60 volts times 8, times 35 volts over 60 volts. They scale what's called linearly. So that's actually 8 times 35 over 60. Okay. 8 times 35, 240 plus another 40, 280 over 60, 28 over 6. Shucks if I know. Let's see. 8 enter 35 times 60 divided by 4.67 Newton meters. Alright, there we go. So that's the stall torque. So what I'm going to do is put on 2 new points on there. I'm going to get 4.67, and then I'm going to put 175. I'm going to draw a straight line between them. And that's the line that I get for 35 volts, the second line on there. Now, if I want to know what the torque is at 131 radians per second, 130.8 if you will, here's 130, I'm going to say it's about equal to 1.0, I don't know, 1.1 Newton meters. That's my guesstimate. Okay, here we go. What I'm trying to show is this data point right there, about 1.1 Newton meters. What I'm doing is I'm saying, hey look, you asked me for 1250 RPM, well that's 130.8 radians per second. Come up and intersect that line, tell me what kind of torque I get. So this is the speed right here, and then this is going to be the torque coming across. And it looks to me, like I said, about 1.1 Newton meters. Now, interestingly enough, let's get the power out at that point. Well, actually, first off, torque at 35 volts and 1250 RPM is about equal to 1.1 Newton meters. And just out of curiosity, P out then is equal to 1.1 times 130.8 is equal to 130.8 plus 13.1. Calculator. Enter. Alright, 130.8. Enter. 1.1 times 143.9 watts. Pn is equal to V times torque over K sub A. K sub A was 0.2, and so that's actually equal to 35 times the torque, which was 1.1, divided by 0.2. 35, enter. 1.1 times 0.2 divided by 192.5. There's my P out, there's my P in. My efficiency, my estimate for the efficiency is 0.747. %. Oh well, I guess we'll have to redo it because we got 74.8% the other way. All right, that's my point, is that, you know, you're getting those answers the same both ways. All right, that covers DC motors. That's enough for that.